Infinite square wells. Welcome to the show. By the end of this video, you will be familiar with what the infinite square well is and how to manipulate the allowable solutions. The question of interest here is calculate the expectation value of x, x squared, p, p squared, the standard deviation of x, and the standard deviation in p for the nth stationary state of the infinite square well. Check that the uncertainty principle is satisfied and which states come closest to the uncertainty limit. If you want the notes on the nth state and stationary states, all that stuff, just go to the Instagram and you'll see them in the subscriber section. But what we need to know about this is to solve the time-independent Schrödinger equation, we need to specify the potential. Here, the potential V of x is the infinite square well, which is defined as a piecewise function, where we are 0 for x between 0 to a and infinite elsewhere, as seen next. As you see, the width of the well is a length a. If this is x equals 0, this is x equal a. Our length of, or rather the width of the well is a, where inside we have 0, the potential is 0, but outside, where the gray shaded regions, these are all infinite. These infinite areas trap the particle inside the well, and we need to keep this in mind as we discuss the solutions of this potential. Here, the solution to these time-independent Schrödinger equation yields an infinite set of wave functions, each in a unique state n. The nth state wave function for this potential is given by psi sub n of x is equal to square root of 2 over a sine of n pi over a times x, where a is the width of the well. Now consider the expectation values. The expectation value for x in the integral form, instead of going from negative infinity to positive infinity, goes from 0 to a, or the width of the well. So here we have our typical psi star notation with psi with the operator in between, or the expectation value variable. And we see that psi star psi is both real, so we don't have to worry about any complex conjugates. And then we get the square root squared from both sides, so that's why we get 2 over a here. And now we're just left with this chunky integral where x sine squared of n pi a over x dx needs to be evaluated. This is easily done with the use substitution of n pi over a times x. Here we'll go ahead and solve for x since we have this free variable in front of sine. And then we see we get a n pi times u, where dx is quickly calculated, no big deal. And then, of course, in a u sub, it's easier just to find out the new limits than it is to resubstitute in the values. So here, u of 0, if we plug in 0 for x, we get 0. If we plug in a for x, we get a canceling with a, and we just end up with n pi. Easy enough, we like that. Plug everything back in, we get a over n pi times u from this x substitution. And then sine squared goes to sine squared of u. We like that. Of course, we have some coefficients with the dx term. So collectively, we have a n pi squared that we need to bring out front because they're all constants. Note the new limits from the u sub. And we're left with a u sine squared u du integral to solve. Here, we see that we have a couple factors of a, so we'll go ahead and cancel those out. And we'll see next step why. As for the integral, it can be solved using integration by parts or looked up in a table, but regardless, it yields this antiderivative, which needs to be evaluated with care. As you see, we kind of simplified the a terms here, so that's why we don't have an a squared anymore. But when we evaluate this integral, with the antiderivative rather, what we see is that we have n pi squared over 4 sine of 2n pi and cosine of 2n pi Then of course you plug in 0 for sine, you get 0, so the whole thing goes to 0. And 0 for cosine leads to a 1/8. So we get a bunch of zeros from these two, and a 1/8 from the cosine. Double negative since we have to take the minus lower bound. But what we need to realize that the 2 pi in are all factors where sine is 0 and cosine is 1. So we're going to have to cancel out these as repeated factors here. And we do that in the next step. Color coded, of course, so we see exactly what's going on. Since this goes to 0, that's bye-bye. Since cosine always is 1 there for any factor of n, and we see that we already had another 1/8, we cancel and cancel. So what we're left with is this front running term, which is wonderful. Okay, so we notice here that the n's cancel as well because of this term being the only thing here, and we're dividing by an n squared pi squared, and we have an n squared pi squared. So wonderful, chop chop, and that's what we see in the next step with the cancel bars in red. We also were able to get a factor of a over 2, or rather, we were also able to cancel out this 2 by the a with this factor down here. And so what we see for the expectation value of x is a over 2. And this is independent of n for all n. How cool is that, given that n has been everywhere with these stationary states? What should be noted here is that this is the expectation value, and it is the center of the well. And that kind of makes sense, doesn't it? Even though it is a statistical measure. So another thing to help your intuition, and we can check ourselves with that. So here for the expectation of x squared, we are using the same substitution again. And from the one before, so here we plug everything in. Note that with x being a square factor, here we have the coefficients squared times the square factor, or times the coefficients from the dx term. So that's why we have an a over n pi cubed this time. And then of course we cancel out a factor of a with an a from the a cubed, and that's why we end up with 2a squared. Again, look up in the tables, things of that nature, and find this antiderivative. Now note here that with what's attached to sine here in the parentheses, we know that sine from last time with any possible connection to n pi is going to go to 0. And of course sine of 0 is 0, so this whole segment here in the middle is going to have a multiplied by 0, so this parentheses is going to go away and we will not continue calculating with it. Now what we will continue to calculate with is the cosine and leading term. And our first step is attempting to cancel the n pi cubed factor out in front via factoring the numerators in both of these fractions. To do this, we must multiply by, quote, 1 in front of the n pi squared, well, in the form of n pi squared over n pi squared, which is what we do here. Okay, we're allowed to because we know multiplication by 1 yields the same result, so we're good. But what this is doing is giving us a factor of n pi squared times n pi, so we get an n pi cubed, which we can factor out here, and as you see, a lovely thing happens and we can cancel. Wonderful, wonderful, wonderful. Get rid of it while we can. We also note here that we can pull a factor of 1/2 out of both of these things since we're dividing by 6 and 4, so we did that here in red. That's why I color coordinated there so you could see that I was pulling a factor both n pi cubed and 2 out at the same time, and we simplify it down. And this shows here that the expectation for x squared is a squared times 1/3 minus 1 over 2 n pi squared, and this has a factor of n here. So let's be aware of that. That will come back later. Thank you to Ehrenfest, we can save ourselves time using his theorem, and the expectation of momentum is equal to m times the time derivative of the expectation of position, which of course does not vary in time, so that goes to 0, and that's a lot simpler than these integrals. However, we have to use, if we needed to check the integrals, we would have to do what's called a orthogonality check, because that derivative that is the momentum operator would act on the state of psi, psi n, which we know is sine, and the derivative of sine goes to cosine, and cosine and sine are orthogonal functions, and so either way we're going to get 0. So that would be a good check for you if you want to try it yourselves. Now, for the momentum squared, the operator has to be squared as well, and we're going to use a slightly different approach to save us some time. So here we note that the operator h bar over I dx d by dx squared has to be in effect, so we factor out the h bar over I squared, and we see that this derivative, the double derivative, has to act on the state vector psi n. So with that, I color-coded it in green for a reason, because this is the left-hand side of the time-independent Schrodinger equation, and we could substitute that in. Why do we want to do this? Well, not only do we get to see what cancellations occur with the h-bars here, love that, and notice that I squared is -1, so the negatives cancel as well. We get to bring into the fact of the knowable energies, which makes simplification easy. We can bring it all out front, and more importantly, instead of having to take two derivatives and get a bunch of constants, we can just go back to the wave function itself, and now we have our orthonormal condition here due to normalization that we could use. And so we bring all these terminologies down, and we see we get 2m, which is right here, the allowable energies for the infinite square well, which is n squared pi squared h bar squared all over 2ma squared times 1. The 1 comes from the integral being the normalization condition. And so we see the mass term cancels in both of them, which is really cool. We don't have to worry about mass here, so the particle mass is a non-factor. But what we see here explicitly is that the momentum squared expectation yields an n squared relation 2 via n pi h bar over a squared. So both of these square expectation values rely on n and a, as we see in these two boxes. Pretty cool. And we'll have more on this soon, but the substitution method here definitely is faster, in my opinion, than what it would be taking two derivatives. So keep in mind, we have tricks for the trade. And finally, it's time to compute the measurement variations and find their product. So here, what we're going to do is find the variation, or the variance, in the position side of things. So that'll be the expectation of x squared minus the expectation of x, the whole thing squared. As you see, we just had a over 2, and we got to square it. Much different than what we had in the expectation x squared part. We are going to try to get this a squared out of both. So notice that a over 2 squared here yields a squared over 4. So this minus and this 2 squared show up here inside the bracket. Again, we're trying to factor the a's out since we know we're going to have to take a square root soon. 1/3 minus 1/4 gives me a 1/12. Notice here how I have a factor of 4 here, because I can have a factor of 4 times 3. Have a factor of 2 here, so by using the multiply by 1 trick, I can put in another factor of 4 in the denominator, only to factor that out, which is what we see here. Cool, cool. We do all of that for the sake of the fact that we're taking a square root here, and that is easily simplifiable and leaves us with a, pretty easy to deal with square root. In a similar manner, momentum's even easier to deal with in finding the variance, because one of their expectation values was 0, the other was a square, so taking a square root yields to n pi h bar over a. That's not too bad. The integrals were definitely bad, but this one is not too bad. Now their product, of course, is what is of interest. So the standard deviation x and the standard deviation p, multiply them together. What an interesting fact here that the a cancels. We do not have to worry about the width of the well at all. But what we do see here is that we have an h bar that floats, and we're going to put that up front, so we get some h bar over 2, and the square root is a multiplicative factor. And the reason for doing this is it makes it really easy to compare values to the uncertainty limit. Okay, we like that. And so what we do is we take the 𝑛⁵ from right here and push it in. How do we push it in the square root? Well, you square it and then distribute to both terms. Hence, the 1/3 goes to 𝑛⁵ squared, since we have to square it since it's on the outside of the square root in order to put it back in, over 3. And then this factor of 𝑛⁵ squared cancels when we push that in and distribute. So again, we make this a multiplicative factor simply because it makes it easy to compare to the limit of the uncertainty. So for our base case, this is going to be the closest approximation to it, and numerically we see that it's 1.136 h bar over 2, which is indeed greater than h bar over 2. Why do we know that this is going to be the closest to it? Well, if you note, the leading term in the square root is n squared pi squared over 3, and so if that number will keep getting bigger as n increases, and the difference of 2 makes absolutely no difference in the behavior of large numbers. So what we need to do is find the smallest n possible for the solution set and use it here. And that's what we do. And of course this number is pretty close to the limit, but it's still greater than. So we are safe with the uncertainty limit. And to bring things full circle, thank you for watching the video. You can see here how the infinite square well leads to a very specific type of wave function, and the allowable states are something that need to be tested on for the sake of things like orthogonality and what is allowable. Recall from a couple questions ago how we can add multiple of these states together due to being able to have linear combinations also be admissible. So be on the lookout for that, and I will see you on the next one. Until then, happy learning.